So now that we've discussed a bunch of different model architectures, you might be wondering, are these models any good? Well, in this video, we're going to be talking about data sets and evaluation metrics and see how these models actually perform. And then we're going to wrap up this video by talking about remaining problems. For training models, we typically use the Open Catalyst 20 and 22 datasets. The reason for this is we wanted to explore how well our models would generalize if we trained them on a lot of data. There are 140 million examples across these datasets, and it took a huge amount of compute to compute them. It is available with an open source license that allows for both commercial and non-commercial purposes. And finally, we created several different splits of the dataset, the 200K, the 2 million, and the 20 million, in case you wanted to evaluate your models against, other approaches, but you didn't have enough compute to train it on the entire dataset. So what's in this dataset? Well, it's essentially a bunch of atomic relaxations, where we have an initial structure, which is a catalyst surface and an absorbate, and then we perform a relaxation, where we first compute DFT to estimate the forces and the energy of the system. We then use those forces and an optimizer to then update datum positions. We repeat this, compute DFT, update datum positions, repeat, until the forces go to 0, and we find our relaxed structure. Now, there's several different tasks that are related to this problem. The first one is what we call S2EF, or structure to energy and forces. And what this takes as input is the structure, and then you just have to compute the energy and the forces. And this is the problem we've been talking about this entire time. And here we can just evaluate the accuracy by looking at the mean absolute error of the computed energy and the computed forces. The next thing that we could evaluate is, can we compute the energy of the relaxed structure? Because this is a property that we really care about in a lot of practical applications. So there's two different ways that we can compute the energy of a relaxed structure. The first is we can just take the initial structure as input, and then we can just compute a scalar value that we think is going to be the relaxed energy given that initial structure. The second approach, which we call the relaxation approach, is we use our machine learning model as a replacement for DFT. So here we take the initial structure, we use our ML model to estimate the forces, we then update the atom positions, compute the forces again, update atom positions, repeat until the forces go to 0, and then we use the ML model to estimate what the energy of that relaxed structure is. And in general, we find that this second approach is generally more accurate than just computing the relaxed energies directly. Another task is to take the initial structure and compute the relaxed structure. And this, again, can be done either way. You can either take the initial structure and directly compute the relaxed structure, or you can use a relaxation-based approach. So you can use, again, your ML model as a replacement for DFT. You compute the forces, and then update datum positions, and repeat that until you get a relaxed structure. If you train a model and you want to see how well it's working, we do have the Open Catalyst leaderboard. You can upload your results there, and you can compare on the test set, which we don't give away the ground truth for, against many different state-of-the-art models. Now, if we look at the progress of models over the last 4 or 5 years in estimating the forces, what we see is the following. So the early models, such as Chenet, which I showed earlier, have fairly high errors of 49 millieV per angstrom. But then the next generation of models over the last 2 to 3 years, we've seen a steady improvement in accuracy. And then more recently, some of the equivariant models have even improved accuracies even further. Now, what's really exciting is that if we look at relaxations performed using DFT or using ML, in a lot of cases, we'll see that they're quite similar. Like, these machine learning models are beginning to show some really good promise in being able to estimate forces in a reliable manner across many different types of catalysts and absorbates. And in this example here, you can see it's a fairly complex system, and the machine learning model here, ESCN, does a pretty good job of estimating the relaxed structure. Now, obviously, it's not always going to work. Here's an example where a machine learning model fails. If you look really closely, you can see at the end, the little hydrogen atom there pulls away from the rest of the absorbate, and this is an error. Using these machine learning models, we can perform relaxations given an initial structure. But what we really care about in practical scenarios is, given any possible placement of the absorbate on a catalyst surface, which results in the minimum global energy. So by using a machine learning model, we can perform a large number of relaxations, let's say 100, by just randomly placing the absorbate on top of the catalyst surface.
And then we can find just a few of them which result in the lowest energy as predicted by the machine learning model. And then if we want to have higher accuracy, we can then perform a DFT calculation just on the relaxed structure that the machine learning found. And by using this hybrid machine learning and DFT approach, we can basically calculate absorption energies, 700 or 1,000 times faster. But the real question is, are they more accurate? And here what we're doing is we're plotting the force MAE of the models on the x-axis and the success. And that's like, is it within 100 millieVs in estimating the energy? We see that the early models didn't do that good of a job. The success rate was quite low. The next generation of models did a little bit better, but the most recent generation of models is performing quite well. Close to 90% of the time, we're actually getting results that are within 100 millieV, which is a fairly small amount of error, of what you'd get if you computed them using DFT. And to help out the rest of the community in using these techniques and using these technologies, we released the Open Catalyst demo last July. So if you want to check it out and see how it works, you should go there and check out these models in action.
If you're looking at what I just said, you might be thinking to yourself, are the models good enough? Do they even need to be improved further? Well, the answer is yes. There's still a lot of work to be done. So let's talk about the remaining problems. When we perform a single relaxation, what percentage do you think are actually successful? That is, what percentage of the relaxed energies computed are within 100 millieVs of what we would have gotten with DFT? What do you think? 70%? 50%? Nope. It goes all the way down to 16%. It's not zero, which is where we started, but we still have a long way to go.
The second problem we face is we don't know if a ML model is correct or not. If we look at these different relaxations here, they all look good to us, but only half of them are actually correct. And the ML models, as all ML models and LLMs, etc. today, they're always overconfident in their estimates. And if we had a way of determining when the ML model is correct or when we think it's going to be wrong, that would help a lot in getting these models adopted and being useful in practical situations. Next, the structures that we've been modeling are really simple. It's this clean catalyst surface with a single absorbate on top. But in practice, it's a lot more complex. The catalyst surface, might not be perfect. It might have, different atoms sitting on top of it. It might not just be a single absorbate. There be multiple absorbates that are interacting with each other. And in many practical situations, you don't just have an absorbate by itself, but it's in a solvent like water. So you also need to model the water molecules that might be interacting with the absorbate and the catalyst surface. And finally, reactions in nature happen super quick. But if we want to do experimental tests, these are really slow. If we do DFT simulations, they're a little bit faster, but still really slow. Now, the machine learning models are great because they, speed up how fast we can compute estimates for these reactions significantly. But there's still a really big gap between how fast our ML models are and how fast reactions are in nature. So it'd be great to have much more efficient machine learning models to use to estimate our computational properties.
All right, that's a wrap. I really hope you enjoyed these videos. As you can tell, I'm super excited about this space, and if we can work together and improve these models, just think about what we can do. We can gain, a deeper understanding about how our world works at the atomic level. And if we can do that, hopefully we can gain insights into, a lot of different applications, including important ones like climate change. So if you're excited about, looking into this more and getting involved, go check out the Open Catalyst website and check out our GitHub repo. I'll put links below.